So tonight's talk is going to be on blockchain. As Kim mentioned, I'm a Xamarin developer, so blockchain is a hobby of mine. So I can't say that I'm an expert in blockchain, but I have learnt a whole lot. Coming from a Xamarin background, I've decided that I really need to understand this because I can see the potential in it. And what I'm hoping to get across today is that you can understand the potential of it. I'm going to cover some programming aspects, but that's not so you can learn how to program, because I don't have time. It's so that you understand, so I can take a bit of the mystique about away from this. So I'm going to cover what is blockchain for, how it does it, what it's not, and a little bit about the Ethereum network. I should mention that there's a lot of slides here. I'm going to rush through them fairly quickly and probably appreciate questions at the end. So save up your questions, simply because I've got a lot to get through. This slide pack, I'll make this available. There's a whole bunch of slides that I won't touch. So if you are interested, it explains what Metamask is and what Web3 is and those sorts of things. I'm not going to go through them in detail in the presentation, but they're there on the slide pack for your interest later. There are lots of networks and lots of blockchain networks. I'm only picking the Ethereum one. The capabilities that are available on the Ethereum network are the same or similar in all the other networks, like Bitcoin, EOS. Ethereum is not my preferred network, but it's the most popular network. So it's probably, and as a consequence, it was easier to learn, and it's because there's a lot of tools and facilities available on the Ethereum network. Secondly, the Ethereum network is a proof of work network, not a proof. There are two other types of consensus models, one called proof of stake and delegated proof of stake. Now, they're actually really important concepts, and I suspect we won't have time to go through what the differences are. Ethereum and Bitcoin networks, they're proof of work networks, so therefore they use miners to do their authentication. The proof of stake networks are slightly different, but it's exactly the same concept. Understanding what the Ethereum network does and the proof of work network will make it easier to understand later. A bit of theory. So history. Satoshi Nakamoto, he created a thing called the Bitcoin white paper in 2008. So the purpose for him was to be able to transfer currency without a central authority. And these concepts I will reiterate through the presentation. But many people realized that it could be used for a lot greater purposes. Now, Vitalik Buterin created the Ethereum network in 2013. His purpose was to create a more generic, so people could use his network, Ethereum, to be able to create multiple currencies, not just Bitcoin, and to be able to use it for not just the transfer of cryptocurrency. He was the one that invented the smart contract, which is the main subject that we're going to go through tonight. So what's it for? The blockchain is for the transfer of assets digitally. Let me explain with this example. When I copy a song, maybe it's my own song, and I distribute it to AJ, and AJ distributes it to Kim, and Kim distributes it to Emmett. Each of those people have an equal copy of that document, that song, so they can all play it. Now, if I was to transfer currency, I don't want that. If I gave a coin if I bought something from AJ and gave her a coin for that, I don't want to have the ability to use that coin again. So what we're trying to do here, what the blockchain gives us the ability is to transfer assets so that I can't use it anymore. So that makes sense, and it's easy to explain with a coin because, yeah, that example's straightforward. But we can use it for any asset. So a classic example is me being able to sell my house, to be able to transfer my house to someone on the other side of the world, reliably, irrevocably, undisputed, and instantly. So the ability to be able to do that on a house, on your power that comes from your solar system. Can't think of examples at the moment, but anything that you can transfer now physically, you can theoretically transfer with the blockchain, and that is why it's really important. The other thing that it gives us is smart contracts itself. So a smart contract has a value. For example, it's being used by an Australian company whose name escapes me. They're using it to record election vote. What do we call it? Election. Yeah, to record all of your preferences in an election. So instead of going into a polling booth, filling out a piece of paper, putting it in the slot. No, actually, instead of walking in, registering your name, getting a number on it, filling out your thing, putting it in a post box, someone then has to grab that, read it, validate that it's true, make sure there's no duplicates, and check and double check. So instead of doing all that process, if you've got a smart contract to do that, you can do that instantly. They're suggesting that in a fairly reasonable election, instead of costing, maybe it costs us $20 million to run our national election, they're talking about $1 million because of the saving processing and do that. And because it's indisputable, it's a perfect example. The other benefits are that the network is a distributed network. So because of that, you can run programs in a distributed manner, which is available for large corporates, but it's not necessarily available for small organizations. So assets are currently distributed in two ways. So I gave the example of a coin. So I physically give AJ a coin. I don't have it anymore. Now, that's not the only way that we distribute money. Obviously, if I transfer money to AJ via an online service, that's a digital transfer of money. Now, and that's what we're talking about here. But the difference between what we do today and what the blockchain offers is that what we do today is centralized. The blockchain offers a decentralized mechanism for doing the same thing. The difference is this. When I transfer money, if AJ was in the same bank as me, both in Westpac, I can transfer money to her and it will happen instantly, and it's trusted and it's proven and it's real money and she gets the money instantly because there's an essential authority that manages both her account and my account, and that's called Westpac. When you've got a different bank and I'm transferring to a different bank, you have two central authorities. So maybe Bank of America. So you have the Bank of America as one authority and Westpac as another central authority. The reason why it takes 2 days, 3 days, a week, sometimes a month to transfer money, especially large amounts of money, across to the other side of the world, to the Bank of America, is because those two central authorities don't trust each other. The banks, so what blockchain offers is an indisputable transfer of money where there isn't a central authority. It's a distributed authority. So you still have an authority called a consensus model that makes it indisputable, but it's for anything. It's across banks, it's across water authorities, it's across electricity authorities, it's across the world. And that example is why the banks are spending so much money in investment into blockchains, because they want to solve that problem of distributing across banks. I quickly want to go through a bunch of terms because you need to understand these terms. I have a glossary of terms paper which has 10 times as many as this, but these are the ones that are relevant for today's presentation. So firstly, what is a blockchain network? A blockchain network is a bunch of computers sitting on the internet that talk to each other. The blockchain, and they run a node, which we'll come to in a moment. A blockchain is a bunch of blocks that are collected together and are chained together by the way that they're encrypted and hashed. A block is a collection of transactions. So a transaction is me transferring money to Glenn. That's a transaction. A block is a collection of those. So might be 10, might be 100 of them all together. They're all hashed and connected. Those blocks are connected one-on-one to form a blockchain, and they sit on the blockchain network. Every node on the blockchain network has a copy of every transaction, every block and every transaction ever made for that network. So at this point in time, if you had a look at the blockchain network for Bitcoin, you will find every transaction ever made and all readable. I can read every transaction that was ever made on the blockchain network. Sorry, the Bitcoin network. A smart contract is the computer program that runs on that network, and the running of that computer program creates transactions. So I would write a smart contract to be able to transfer money from person A to person B. That contract is actually encoded as a bytecode and put on the network, but it's reversible. You can reverse engineer those contracts, so you can see, when I write a program, you can see what that program is and what it does. That's actually not easy to do. The layman can't do that, but you have to be aware that it's not intended to be hidden, what those programs do. A miner is a person or an organization that has a node on the network, so they have a computer on the network, and they're the ones that validate the transactions. So they get paid to provide the service of this distributed authority of whether this transaction is correct or not. Block time. It's sort of unrelated, but it's sort of related. In the proof of work network, there's each of the networks, so Ethereum and Bitcoin networks as an example, they have this thing called block time, which is 15 seconds for Ethereum and 10 minutes for Bitcoin. What that is it takes 15 seconds to approve a block. That's it. It's always 15 seconds. As technology gets better, it will always be 15 seconds, or an approximation to 15 seconds, which I'll come to later. Consensus. So consensus is, as per the English word, it is you need 51% of miners to approve a block for it to be treated as valid. A consensus model is, I mentioned before, there's proof of work, proof of stake, and delegated proof of stake. They're the main ones. In fact, I suspect they're the only ones, but certainly the main ones. I'm not going to go into detail of those. If we have time at the end, it's quite an important concept, and a lot of the criticisms about how much power the blockchain uses is going to disappear because of the movement away from proof of work to delegated proof of stake. So we're seeing lots of evolution happening in this space. And a distributed app, a DApp. These are a solution to a problem that uses a blockchain smart contract. Normally, it will have two components, well, three components. The blockchain actual smart contract, which I'll show you one in a moment, is a small component. The bigger component is the business logic and the user interface logic that sits above that. All of these terms I'll reiterate in examples as I go through. Human nature. People are the ones that make the blockchain work, and people by nature are greedy, dishonest, and really bad about making decisions in a consensus or a corporation. Satoshi knew this, and his solution, which is what makes it revolutionary, he relied on this. If people were not greedy, they weren't dishonest, and they could make decisions really quickly, then blockchain wouldn't be needed. For the blockchain to work, it needs to be immutable. So that means that once you've agreed on a transaction, it can't be changed. It also needs to be trusted. So when you agree that this transaction is correct, there must be a consensus that it's correct. And there needs to be, this last one, a little bit unintuitive. It needs an algorithm that runs on greed, runs on the nature that people are, because we need to get people out of bed in the morning to actually approve the transactions. And Satoshi uses greed to do that, or the proof of work model uses greed to do that. People want to make money, they want to try and trick the system, they want to no, I'll stay there. More that they want to make money. So, how it works. Tim has 3 transactions, each of 4 coins. And what he wants to do is he wants to give me 15 coins. What miners do is their job is to validate that situation. Now, obviously, they would say that's invalid because he's only got 12 coins and he wants to sell me 15. So if these were actual Bitcoins, that's a lot of money. But they're actually tokens, which could be Bitcoins, could be Ether coins, they could be anything. So there's 3 problems with this. First of all, what's to stop Tim going out to all of his miner friends and saying, hey, you should approve this because, and I'll give you, you know, this could be worth $1 million, and I'll give you $100,000 each if you go and approve this. So the first solution to that was Satoshi said that you need 51% of all of the miners in the world to actually agree to this, that this transaction is valid. The second problem is, why are these people going to get out of bed in the morning to go and validate these transactions? And we do that by paying them money. And I'll cover where the money comes from in a moment. And the third one is, there might be, just say there's thousands of miners and there's actually many, many more. Who gets paid? If every one of them got paid, then the amount that they got paid would be really quite small and it wouldn't satisfy problem 2. So basically it's, we give them a technically difficult problem to solve. It's actually not. It's not technically difficult, but it's costly to solve. Something that takes a lot of electricity, a lot of money. And if the first one who approves the block or approves the transaction is the one that gets the money, basically. And if they're dishonest, they lose that money. Now, there are a number, not lots, but there are a number of problems that the blockchain solves. I'm not saying these are the only ones, but these are the key ones for this presentation in order to understand what this blockchain thing is. The first one was, back here, is that the blockchain needs to be immutable. So how they do that is each block, as I mentioned before, a block is a collection of actual transactions, say transactions to transfer money. Each block is hashed, so they could use SHA-256, which is a hashing algorithm that I'm familiar with, but Ethereum actually uses KEKAK-256, which is SHA-3, but whatever, it's a well-known hashing algorithm. In the header of each block is the hash of the previous block. So I have a block, I hash it, I get a number. The next block, they take that block and they put it in the header, and then they hash that and they get a number. If you change this block, then that hash will be different, and that means that it will carry on forward. It will now make the next block invalid. So if you have 20,000 blocks all in a row and someone goes and says, well, that wasn't $10, that was $10,000 on this transaction, if they actually go in and change it, which anyone can, all subsequent blocks will now be invalid and they all need to be redone. And that's what makes it immutable. That's actually, so physically you can do that, but there's a lot of work and it's just too difficult because somewhere along the line someone's going to say, well, no. At every step you have to get 51% consensus that this is correct, and you won't get that if you've got 1,000 blocks to correct. And that's what immutability is. Now the other two components were, I'll quickly switch back, were the blockchain needs to be trusted. So there's actually two parts to that. Part one, consensus algorithm. I think I probably already explained this well enough. What happens is, so we're all familiar with programs in layers, machine layers, assembly, Objective-C, go to 3G languages up to Xamarin. So we compile and we deploy an application to the network. Then what we do is we effectively crowdsource that that block is valid. Actually, I probably haven't explained it very well. So we compile the application to the network and we run that application, which generates transactions. Every one of those transactions, or every bit of data that we put on the network, we effectively crowdsource people to say they're valid. So it is this process back here where the miner's job is to say, all right, 4 plus 4 plus 4 is 12. He's trying to sell 15. No, that's not valid. So we actually get people to do that, and they're called miners. So it's a little bit counterintuitive because as an IT person, I'm more familiar with the idea that you write a program and you run that, and that's all that needs to happen. It'll either work or it won't. But in this case, writing the program, I'm about to show you a Solidity program, and actually is not enough. I can run that, I can generate a transaction, but that's not enough. People have to go in and approve that transaction, and that's the job of the miners.
You're not talking here about physical people.
I am originally, when Satoshi invented this, it was original people. People that had to actually get out of bed, go and sit at their computer and approve it. Technology has moved along a lot further, and now you can even buy hardware devices that sit there and do the approval. But Yeah, that is the concept. So now it's not real people.
Imagine that every transaction is unique to the program. So if I'm doing a contract that says I'm selling a house to you, it's different from your contract, which might be selling a car to me. Different context.
Correct. So the concept here is that if you're selling a house to me, there's a transaction. There's two parts of that transaction. One, I get the asset. Two, you get the money. That
Two transactions.
There's two transactions. Yep.
And those transactions are referring to objects that are different to if I'm selling a car.
Correct, and that would be a different set of transactions. The job of the miner is to prove that pair, you're getting the house, I'm getting the money, that bit is valid. That you had the money, you had the house to give to me to start off with, and I have the money to give to you, and that this is a valid agreement.
So if I'm sitting over here and I want to have a miner, if I want to be a miner, then I have to have some way of knowing that that Jim over there is trying to sell a car and Freddie over there is trying to sell a bunch of flowers.
Yes.
And then not until you open that transaction is you can tell that you can see that there were two different things.
It's kind of not like that. It's the smart contract does that for you. That's what a smart contract is.
Tries to.
It knows that it's a car for money, and there's a different smart contract that knows that it's flowers for money. Let me continue.
Yeah.
The second part is stake. If I was getting paid 10 cents to write a Xamarin app, I probably wouldn't do it. But if I was getting paid a lot of money to do it, I probably would. So, and conversely, if I did the wrong thing and I run the risk of losing money, that would influence what I do. So that concept of me as a person having the stake in the game is the other part of what makes the blockchain work. What we do is we actually use both of these. So the person the miner who approves the block, the first one who does that gets what we call gas. It comes from the American term for petrol, and transaction fees. And it's a worthwhile amount. I'll show you a block in a moment, and we'll have a look at how much that person got paid for that block. I'll show you that. Also, it costs that miner a lot of money to actually run his program to validate the block. He's got to run a computer program for 15 seconds continuously, flat out, to solve a cryptographic problem. That uses a lot of money, a lot of electricity. So if he approves something and he can't get, and 51% of the other miners don't also approve it, he spent all that money for nothing. So he won't get paid for that. So if he continually does that, he's going to rack up his bill and not get any money for that. That's not a good way to run a business. So that having a stake in the game is the second part that makes a transaction, makes the blockchain work. Now, we're going for time. How mining works. There's a link here, a YouTube link from this guy Anders, and it takes about 17 minutes, and it's a really good explanation of how it works. So he's actually written a program and he runs it for you and he shows you what happens. Basically, you grab a block and you hash it, and when you hash it, you get a number. And what you do is you continually you hash the hash, you hash the hash, you hash. You could do that thousands and thousands of times until the first digit is a 0. And then you do it again and again and again and again and again, maybe another 100,000 times, and the second digit's 0. And you keep on doing that until the number of zeros at the front is, the number of digits at the front is a 0. Now, it's a hex number of about 24 characters long, I think. I'll show you one in a moment. But so obviously, as the leading characters are 0, the number's getting smaller and smaller. What happens is the blockchain authority, or the smart contract that runs the blockchain, so the one that runs the Ethereum network, it's got written into it that test needs to take 15 seconds. It's called the block time. For the Bitcoin network, it's 10 minutes. And what happens is, as our technology gets faster and quicker and more intelligent, we can hash hundreds and thousands of times quicker than we could when we did it with a program that I wrote in PHP on my computer. But what happens is the Ethereum network works out what the average time people are taking for to hash these blocks, and they're decreasing the time continually until it's 15 seconds. So it might be 17 seconds, it might be 13 seconds, but they're always looking at what are people doing at the moment, what's the average, let's make the number smaller to get it to 15 as quick as we can, 15 seconds. That's basically how it works, and as I'm sure you're aware, it's just a standard hashing algorithm. It's not that complicated, but it requires a lot of power. I suggest you have a look at that link if you're interested. Ethereum. So I'm going to show you an Ethereum block. Now, what I mentioned before is that every block on the blockchain is available for everyone. So therefore, this block number 5,454,817, that block will always be the same. When I look at it this time, 10 years time, it will still be the same block. So I'm going to have a look at that particular block, and it could be any block. I can change that number. Oh. Where did my page go? There it is. So let me So this is the block. Now, this is just random. I can go to the next block. You can see here, so I can choose any block that we like, and we should be able to. So let's look at this one. This one was done on this date, 17th of April. There's 187 transactions in that block and 14 contracts. Is that better? This is the hash of that block. Oh, wait on. No, that's the address of the block. This is the hash or the address of the parent block. And this is the address of the person that got paid the money for agreeing to that block. And his name is Ethereum, and it took him 46 seconds to do that particular one. So you can see that I mentioned before, the aim is 15 seconds. Obviously, he's got a slower computer. The difficulty is that number. That's how many times he hashed that block in order to approve the block. So that's a big number, but he took 46 seconds to hash that many times. That's where his cost is. That's where his electricity cost is. And total difficulty, I don't know what that is. It's 29K. The block, it's a small one. He got paid 7.9 million which is a 10 to the minus 18 of an ether, and that is about, oh no, sorry, here's his, oh no, he's also got a block reward as well. So he got 3 ether block reward, which is an ether's about $200, so he got $600. $600 plus this gas, and that's about all I can tell from that. And what I can't tell from that was what the transaction was about, which comes back to your question. Oh, of course, I can have a look at the transactions. So here are the transactions. So this was a transfer from this person to this person of 0 ether. Look at the second one. This was a transfer of this from this person to this person. That's their wallet addresses of 0.05 ether. And it's in the block number, that one, which we know, etc. Let me go back to the presentation. When I get to the next slide, you need to know that there's actually 4 Ethereum networks. So there's the mainnet, what they call the mainnet, which is the production network, and then there's these 3 test network. I'm using the Rinkeby network, and I'm using the Rinkeby network because it costs money on the real network. Now, we have emulators, we have test networks, and we have the mainnet network. Emulators don't have miners on them. So therefore, when I do a transaction, it happens immediately, which is great for development, not so good for testing how your user interface works. The Rinkeby network is actually real people, real miners, doing the same stuff as on the Ethereum network. I don't know how they get paid, I don't know how it works, but it does work. A transaction, transaction has these fixed fields. Now remember, I'm talking just about the Ethereum network. So the Bitcoin network is different, the EOS network is different. Each transaction has a nonce, which is the number of times this person has sent a transaction. So the number of times I've used the network. The gas price, which I'll explain in a little while. The gas limit, how much the programmer was prepared, the maximum amount the programmer was prepared for a transaction to cost. Who's the receiver of the network, and the value of it. The data in this field is if you're transferring a currency, I don't know what would be in there, but if you were storing a smart contract on the network, it would go in that field. If you're actually storing data on the network, like not someone's credit card number, but maybe encrypted credit card number, it would go into that field. Anything you store on the network goes into that field. And the VRNS, if you look them up, it just says cryptographic information. No idea. One thing you will notice there is that there's the receiver of the transaction, but there's not the sender. So the sender, so what happens with this transaction is it gets signed, encrypted and signed, and that signature is the person who's sending the transaction. That's why it's not in the transaction itself. I know I'm going really fast, but hopefully it'll all come together in the end. Metamask. I'm going to show you Metamask. So I have a Google Chrome. I've added Metamask as a plugin or an extension to Chrome, and here it is here. I can't grow it up any further. It's this little icon up the top right called Metamask. So when I click on that, you will see that I'm connected to the Rinkeby network of Ethereum. I have a choice to go to the mainNet or the two other test networks, or I can go to a local network, which is effectively an emulator, and there's this other option, RPC, where I can connect to someone else's network. So MetaMask is a tool that someone's developed to help you use the Ethereum network. I have 18 Ether coins, which is worth around about $4,000 on that network. They're all that's all fictitious money because I'm actually on the Rinkeby network, so it's a test network. I can this is interesting. I'll copy my account when you create an account with MetaMask on the Ethereum network. It will give you an address. That address is across the mainnet as well as each of the test networks. You don't get a different address for the different networks. So this address that I've got here, this is when I trade actually, or when I create a smart contract, that will be the address that's assigned to it. Now I just wanted to copy that to the clipboard. I want to show you the format of that. So I just bring up a Chrome command line, or command prompt, and I'll paste it in there. So I don't know if you can see that. I don't think this will expand. Oh, yes, it will. So I've pasted this bit in, which is the hex, and that's my address. I can't remember how many characters it is, but that translates to 9.5 to the power of 46, 10 to the 46. So that is a very, very large number, and that address is obviously going to remain unique for hundreds, probably thousands of years until we run out of addresses. Now, all of these addresses that you'll see are all of this format. In fact, you'll see this format quite a lot, and it's a very large number. That's why. That's one of the reasons it all still works. That was MetaMask. So I'm going to switch into programming, and I wanted to show you a Solidity project and a user interface project, so a solution that has both a Solidity component as well as a user interface component. And later on I'm going to cover Xamarin and using Xamarin or .NET in general to be able to access this. But before I do that, does anyone have any questions? I can only take a couple, but any questions so far?
I was wondering about privacy.
In what context?
Of the senders and receivers.
I'll cover that. There's a section right at the end that says, rather than explain what you use the blockchain for, I'm going to explain at the end what you can't use it for. And something that transactions have a particular privacy problem, you can't use the network for. So I'll cover that, Greg. Any other questions?
What dictates the price of all these tokens?
There's a short answer, there's a long answer. The short answer is there's two components. There's actually three. there's a component for starting up a network. So to get people involved, you need to give them a bit of extra money. So putting that one aside, there's gas, which is calculated by how complex your Solidity program is. Then there's transaction fees. Transaction fees are how quickly you want your transaction to be approved, or how much effort that you want to go into your transaction. As time goes on, as this technology becomes more and more mature, I'm sure it'll get to the point where you want your transaction done in microseconds and you pay more money. You want it to happy to take 2 seconds, then you pay a standard amount of money. That's how the money comes about.
Is there a quick answer to your understanding of why Bitcoin takes 10 minutes and Ethereum 10 seconds? It's quite a large time difference.
Yeah, it is. Bitcoin was the first. The thing about blockchain is that it's very, very hard to change. So Bitcoin made a few mistakes. One of them, I believe, was that their block size is too small, so they can't approve lots of transactions. I think I don't actually know, from what I've read, because I'm interested as well. From what I've read, it's because that was the decision at the time. Yeah. There's no technical reason why Ethereum takes 15 seconds. Just to put it into context though, this is a problem. 10 minutes. Well, actually it's 10 minutes to prove a block, right? But you need a number of blocks to be confident that it's going to go through. So you need, maybe they're saying on the Bitcoin network you need 6 blocks. So that could take up to 60 minutes to get that approved. But just remember that when this was first invented, it was taking, a week to do a transaction across the internet. To transfer money from here to America, it was taking a week. And now they've got it down to 60 minutes. That was a massive, massive improvement. So now we're at, well, wait on, 15 seconds is too long, or 3 minutes on the Ethereum network is too long. But really, in context of the problem they're trying to solve, it's 1,000 times better. Last question.
Is there a lower limit to how quick it could be? Like if I made my own network and I said I want it to be half a second, is there something stopping me from doing that?
There's 2 answers to the question. First answer is that there is a physical limit of how long it takes to hash. So the longer your blocks, the more it takes actually to that hash. And that has an influence, but nothing of the order of 15 seconds or 10 minutes. Second answer is that you want to get people to get involved in your network. So if you built your own network, you've got to get them to approve. And part of that is how many people you get involved, how difficult it is to solve the problem. So if you make it really, really easy to solve the problem, then you're going to run into lots of trust problems because people are not going to believe that the transactions are valid. This problem is probably better solved by, rather than going down the route of proof of work, which is the miners and the approving of the transactions, is to go down the different consensus model, which is delegated proof of stake or proof of stake, which we can discuss later. All right, let me move on. So I'm going to talk about programming. The technology is actually really simple, I've found, and each of the components of the environment is actually quite simple too. It's just that there's a lot of them. And whenever you've learned a new language, it takes a while to get your mind around all the different components and all the different tools you need. This is no different. As I've mentioned before, there's a whole bunch of terms which I'm not going to go through, but they're in the pack. This is my program. It is really complicated. It's block Lotto. It's the ability, I'm putting up a page, and you can give me some money, some ether coins to play in the game, and when I've decided that there's enough money in there, I'm going to draw it, and it'll randomly pick all of the people that have entered and give them all of the money that's in the pool, except for my car. Very, very simple. For this solution, there's two projects. There's the Solidity project, which will show you the code for the Solidity program, but I'll also show you the code for testing, compiling, and deploying. The reason why I'm showing you the testing code is because there's stuff that I spit out in there that's really quite useful. And the user interface project. So this is the bit that calls the Solidity, the smart contract. I'm using React, Facebook's React to do that. And you can also use Xamarin, or .NET, which I've got a slide on later. The reason why I've chosen React is because it was easier to show you what I've got and also to explain. A Solidity program is a JavaScript based language. It's been extended to have a whole bunch of contract specific verbs. This is extremely frustrating. The entire blockchain is under evolution and continual change all the time. Everything changes. So there's components that still haven't been developed in the Solidity language, like a fixed numeric type. They just haven't got it. And it says when you look up the documentation, they've actually created it in the language, but they haven't released it yet because we just haven't got around to it. So. And the tools and techniques change all the time. So if what you ran a week ago may not run today because it's continually changing. When you compile a Solidity program, it creates two things. It creates the bytecode and it creates the ABI, which is the JSON. Basically, it's ABI. It's the JSON API. So an API that I have to connect to some network or anywhere. It's that. It generates it for you. And I'll show you that in a moment. In my solution, I have those things. I'll show you them. It's easier. So that's not what I wanted to show you. So this is the React component. What I want to show you is the Solidity. Why is that not showing me Solidity? Window. Lotto. Kim, any thoughts of why? So I have two, or maybe it's behind. So I have two windows of Visual Studio Code. And they both show up in Windows here, but in my setup, I can't see the other window.
Got one over here.
Oh, there it is. It's on the wrong. No, there it is.
You good?
Yep, thanks for that. So this is my project on the left hand side here, my Block Lotto project. I have my contracts, and there's only one, Block Lotto, and then I have the compile, the deploy, and the test code. So let me show you, I've got a little bit of detail here. So this is the contract. Now you'll notice it's 38 lines. It's very small. This is a standard JavaScript type program. So here's the class definition, here's the constructor, here's a bunch of properties. They're all public. Basically, when the smart contract, so this is a Block Lotto smart contract written in Solidity. When the smart contract gets instantiated, it sets up the property administrator to be the person who created it. So in my case, it'll be me, because I'm the person that's starting the block Lotto pool. This format, basically what happens is that on the network, we store the bytecode on the network, and something like React sends a message to it. And in that message, it's who you are and whatever you need to send it. I can't think of, in my case, all I'm sending is, oh no, it could be a transfer. So I'm sending a message of I'm transferring it to this person, and this is the value of my transfer. So basically we send messages to a bit of bytecode sitting on the network. In my case, I'm saying the administrator is the person who runs the contract. I have an administration fee initialized, and I create an array of gamblers, and these are the addresses of the people. So I showed you on Metamask before, that huge number. Everyone has one of those. Now, coming back to Greg's question of privacy and anonymity and that word, I don't know whose address. All I know is this long number. I don't know who that person is, and that's how this works. So this is what allows someone to be a part of this gamble. They could win $500 million, and no one knows who it is. And that's the concern that the governments have around the world. And you'll notice the Australian Tax Department is particularly interested in this component. I have a function that says enter the Lotto. So it says we have to have a minimum value of 0.01 Ether. So you can't do this for less than $2. And if that's satisfied, then the sender, the person who's entering, I add them to the gambler list, and when you send a message to a contract, the balance is automatically managed for you. So I've sent 5 Ether to this contract. The contract itself, or the Ethereum network, or Solidity, will actually manage what your new balance is. So all I have to do for the admin fee is say, whatever the current balance is now, I'm going to take 0.1% as my admin cost. There's another function that says draw the Lotto. Basically, that says generate a random number. Transfer the admin fee. So I take my money out first, and then whatever's left, the balance, I transfer that to the address of the person who entered. So that's to that person's wallet. And then I initialize the list and initialize the admin fee. Oops, pretty straightforward. I have a requirement here, must be an administrator, so only the administrator is allowed to draw the Lotto. And I have an extra function here, and that's to return the list of gambler addresses. That last function is an example of when you write the UI, maybe you need to produce a list of who are the wallets that are in the list. You create a function on the network to do that. That's the entire smart contract. Really, it is just a list of functions and properties to run this contract. You don't have much. So this is a simple one. They can get complex, but you want to keep them as small as you possibly can, because when we calculate the gas, the cost of this, one of the things they do, well, in fact, the only thing they do is calculate how many if tests are in there, how many performs there are, how many calls there are, and each of those they allocate a cost to it, and they add them all up, and that's called the gas. And that's the money that they take out of me. So I've created this contract. So what happens is that contract, the bytecode is created, it's stored on the network, on the Ethereum network in the data field that we saw earlier, but it's stored there under my account. So every time that runs, my wallet gets that gas fee taken out of it, and that's automatic. And if there is insufficient funds, the program won't run. Let me touch on the compile code. So the compile code, there's actually not much to really point out there, other than the compiling process. I've actually hard-coded that. I've hand-coded that. There are tools to do it, but it's really quite simple, and you need to understand how this works. The most important thing there is this. Oh no, this one's actually no. Sorry, it's not the compile. So that's really simple. Nothing out of the ordinary there. But the deploy is a bit more complicated. What's really important here is this. These two lines. This line here. So Web3 is a term that's used quite synonymously with the Ethereum network. It's the set of libraries that allows you to talk to the network. Now, in that case, it's not apparent there, but if I go back to Metamask, so if I go to Metamask and I type in Web3, you will see there down the bottom there that this Web3 is a Metamask injected service. So Metamask has created a Web3, and it's handling for me that I'm connected to the Rinkeby network, and this is my address. So Metamask is a tool that is for testing, really, in that context. Now so Metamask has done that, but in the real world, you need to be able to specify who is the provider, where you're getting your network from, whether it's the Rinkeby network, whether it's the mainnet, whether it's, well, it has to be an Ethereum network, and what are the addresses that you're using. Someone has to talk to the network and provide that information to you. That's called Web3. Specific to Ethereum.
So if you connect into Bitcoin, they would have their version of that tool.
Correct. I couldn't find what it was on Bitcoin, but they must have. You have to have that. It's quite fundamental. And there's other things like you need a hardware wallet provider. There's a little bit there, but this is the important thing. Down the bottom here, these two, that one's probably not so important. I can show you that in a moment. So as I said before, when you compile the network, you can see it does two things, the bytecode as well as the ABI, which is the interface definition. So that actually prints out, that line prints out the interface component of that, but this is the most important. When this builds, it's connected via Web3 to the Rinkeby network. It's going to grab that bytecode that's come from the compile, and it's going to store it in a transaction on the Ethereum network. That bytecode, obviously every time you build this, it's going to have a different address. So this is the bit that says once you've compiled and deployed your program to the network, you actually can't change it. There's actually no way of changing it. So if you've made a programming mistake, it's there. You can't fix it. What you can do is you can trash that one and create a new one, but that causes problems in doing that. So this is quite an important restriction, important to understand. So a lot of you hear a lot of people have made a lot of money out of blockchain with mistakes. That's because the person who thought through the smart contract hadn't thought of all possible combinations. And there are people, programmers, smart programmers, that spend a lot of time trying to work out ways to confuse your smart contracts so that they can make money out of it. And the block Lotto test, what I might do at this point is actually run these programs. Actually, I'll just run the test program. So the test script, basically, this is used a thing called Mocha, but it's essentially NUnit. So you have your parameters, you have your description of your tests, your grouping of your tests, and this is a test. And then each of these are tests. So they are, here's the code, and here's the assertion of what should happen as a result. So I'm going to run that one, and it is, so I'm running it from, what screen do you see? Sorry, I'm having trouble with my mouse. I've actually just run this before just to test that it worked. So it's just a command line. I'm in the block Lotto folder, and I'm going to run npm, which is the JavaScript tool or the node running tool, and I'm going to run a script called test. It's starting up Mocha, that's the tool I mentioned. Takes a bit of time to load. Now, it's thrown out a lot of what looks like rubbish, but I'll explain what it is. So these are the result of my actual Mocha tests. So they've all satisfied as true. If I scroll back, what I have done in the program is said, the very first test is really just print out the ABA interface. Print out, which is there, print out the bytecode, print out a couple of accounts. Let's have a look at that. So the first one was the ABA code. It's just a dump of what comes straight out of the compiler, and it's this, which is a JSON view of all of the functions. So get gambler list was one of my functions. Properties, so pool was one property. Draw Lotto was a function. Gamblers was an array of objects, etc. This is actually quite handy. I'll show you how that works when you use it in .NET. This is the bytecode, so it's actually bytecode that gets produced. And here are two random accounts that have been supplied for me from Web3. And I suspect this very first one is my address. But the main thing I want to show you was this interface here. So now I'll show you the React program. So this is just a standard React setup. There's a tool to create a, I know very little about React, had to learn it. There's a program called Create React App that will just build all this for you. All I've done is changed a few things, but I want to show you this function here, which is block.js. What's in here is the actual hard-coded address. That's the address that my program was loaded onto the network. Without that, it's got nowhere to send the messages to and no way that it'll work. This is the ABI interface. So I load those two as constants in, and then I refer to them within this React program, which is it's a React program, obviously. I'm not going to go through the details there. Oh, you can see that I've created constants, which is the administrator, the function, the get gambler list, get the balance, admin fee, etc. Anyway, the main thing I want to show you is this. So the renderer is basically HTML, and then you pass in your variables, which is very much the same as Xamarin, passing your binding variables. And all these do when it runs is effectively call those functions within the block Lotto smart contract, and they get executed. And every time they get executed, you get charged. I get charged because it's my contract. Let me run that. I've actually got it running on another window here. Oh, no it isn't. So I will run it. It runs it up in my browser on localhost. So what it's done is it's sorry, I will. Can you see it now? So what the program has done is it said, go and put the address, go and put my address of who the administrator is. Now, it would be nice if it said the administrator is Rod Hemphill, but of course everything's anonymous. It doesn't know who I am. So it can only put, the only thing I've got available to me is what the address is of that person. Same if I gave a list of the gamblers, the people who are playing the game, all it will give is their wallet address. Obviously there's no one entered, so I'm going to put in an amount of ether, 0.4 I should say, and enter. Now waiting 6, 7, 8, 9, 10, 12, should be 15 seconds. No.
Have you got that pop up on your screen as well?
Yes. So that pop-up is Metamask telling me what's happening, and you'll see the transaction of 0.4 here. See that transaction? So I've been charged. You'll notice that it's 0.4001224. I've only put in 0.4. Oops, it's gone. The reason why there was the bit at the end is because that's the gas charge. So happens that I'm the person who owns the program, but I'm also the person entering into the Lotto. So it's charged me the 0.4 ether, which I put on the screen, plus it's charged me as administrator the gas charge. And oops, I'll just bring it back. See it there? It's taking a lot longer than 15 seconds. I'm not too sure what's happening. Let me have a quick look. Okay. It says that it worked. So it says that it's resolved. I'm not too sure why. It should have come back saying you've entered and these are one. So one entry, that would be 0.4, of which it would have calculated the fees. So I'm not going to delve into why that didn't work, but it's as simple as that.
Because you wrote it in JavaScript.
So the languages are extremely frustrating. There's a network called Steemit that uses C#. I'm liking that language, liking that network. There's one called EOS, which is the network that I really do like, and it uses C++. God only knows why. So yes, the languages are particularly frustrating. So I think that we've run out of time. We have run out of time. What I would like to, so we don't have time to go through Xamarin and .NET, but I'll tell you this, they're in the slides. There's a product called Ethereum that allows a Xamarin or a .NET program to talk directly in Web3 to the Ethereum network. So there's a link there for that. It's really quite good. It's got a whole bunch of stuff, but one of them's really cute. It will actually, the last point there, will actually generate your C# models and model services from the ABI, which is quite neat. There's a whole bunch of stuff here that explains gas, how it's calculated, Remix, which is a tool, Ganache, which is a tool. There's a few others. I've got a glossary of terms, which I'll publish with this. This will be my finishing couple of slides, about 6 slides. This is the intention of the presentation was to show you what these are, and hopefully they make sense. So the blockchain is not private. In order for the miners to do what they need to do, it needs to be public. This pseudonymity is what Greg was asking about. So this is the opposite to how the banks work. Banks have regulations to say you must know your customer in order to do this transaction, and they keep the transactions hidden from the government. In our case, in blockchains, we make the transactions public because otherwise the miners can't approve them, and we hide the identity of the customer through behind wallets. The bad publicity is about that, not about whether it solves huge problems or not. So this may not be good for privacy. If you want to do something with credit cards, you wouldn't be using them as key information that people could see. There are, with each of these slides, I've got a section down the bottom of what's happening evolution-wise. So there's a project or a currency called Zcash, and they're trying to make advancements in the privacy side. It's not free. Every post costs money. So not like on the rest of our networks. If you want to do a post on Facebook, you don't get charged for that. But if you do want to do a Visa card transaction, you will get charged for that. On blockchain, doesn't matter. Doesn't matter whether it's a financial transaction or not, you're going to get charged. They're very small charges, but they are charges. It is not quick. We mentioned before that there's 15 seconds on Ethereum. Well, can't do that. 15 seconds on Ethereum, and you need about 12 of them, so it might take about 3 minutes to get a valid transaction on Ethereum. There's big changes in this space. Delegated proof of stake consensus model is likely to make, well, it will make huge changes there. Poor throughput. Bitcoin has a maximum size of 1 megabyte for a block, and they're physically limited to 7 transactions per second. Ethereum is limited to 20 transactions per second. If you compare that to Visa, who does 2,000 transactions per second, there's a new, evolution-wise, there's a new network that's just come online called EOS, that they've tested it to 1,000 transactions per second, but they're talking about 1 million transactions a second. Facebook, as a comparison, 5 years ago was doing, actually can't remember, I think it was 40 million transactions a second. Large amounts. It's not flexible. You want to change something, you can't change the program. Secondly, if you want to change the network, so I can create my own blockchain network, anyone can create their own. If you wanted to create your blockchain network and you've got large numbers of miners out there approving things, it's really, really difficult to get them to change how they do things because there's large numbers of them. They might not be online. They might not want to change the way they do things. So if you roll out a change, and we call that a soft fork, if If you roll out a change to your network, then it's sometimes a bit iffy whether it's actually going to get through or not. So it's very, very inflexible. EOS. The other thing is that to make a change to the network, you need to go through there's a governance model to do that. You need to get agreement from the community in the Ethereum and Bitcoin case, and there's changes in that area with the delegated proof of stake. It's not without its limits. Everyone has a copy of the node and every transaction on that node. Currently, Ethereum is 50 gigabytes, Bitcoin is 130 gigabytes, and it's growing at that rate. So therefore, it won't work on a small device. And as it gets bigger, you need more space. So lots of stuff I've covered. There's lots of other topics you can talk about. So this consensus model, proof of work, proof of stake, delegated proof of stake, is something I've mentioned. But there's another one, initial coin offering. So a finance company I saw a presentation of about 4 weeks ago. They've just raised $10 billion through an ICO. The EOS network is the biggest fundraising exercise ever in the world. They raised $14 billion for their network. So there's large amounts of money, and it's quite a different concept to what we've discussed here. But when you talk about blockchain, it always comes up, these huge amounts of money. Now, Kim tells me that the pizzas have arrived. I'll take 2 questions. Great, I won't. No one. Thank you, everyone.